Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. My name is Muhammad Abqari bin Abdul Razak. My supervisor is Associate Prof IRTS Dr. Solehuddin Shuib. Today I will be presenting my final year project entitled Design of High-Flexion Knee Prosthesis using Triz. Let's start with introduction. The knee is the largest joint in the human body, allowing for everyday movement. As we get older, arthritis is the most prevalent disease that causes knee joint dysfunction. It is a disease that affects millions of people worldwide, where it remains the most common indication for total knee replacement. Total knee replacement is a surgical operation in which the knee joint is replaced with an artificial implant to restore damaged knee function. Most knee systems available in the market have been designed to accommodate a maximum flexion of 130 degrees. For Muslim and most Asian population usually require the flexion of the knees to be high as it was part of daily routines such as squatting, kneeling and sitting cross-legged. It became a drawback for the patient that require or wants to have a knee replacement surgery. Triz, which is theory of inventive problem solving, is a problem solving analysis and forecasting tool. Triz as a systematic methodology can be used to generate alternatives in the new product development process. Triz is an excellent tool for design engineers to handle conflicting conditions during the innovation design problem solving process. The figure shows the typical problem solving model based on Triz. Triz usually comprise of few stages before getting the results. One of the most accessible and useful Triz problem-solving method is the 40 creative principles and contradiction matrix table. The Triz theory's contradiction table usually contains 39 design parameters as well as 40 inventive principles for solving the contradictions, which is done by contradicting the feature to be improved with the feature that are getting worse, which then will show the solution from the 40 inventive principles. The principle will be utilized to generate the new concept for the new design. Problem statement. Typical total knee replacement systems in the market was designed to flex to a maximum of 130 degrees. It has become a problem for Muslim and Asian populations which would be hesitating in doing the surgery because the limitation in knee flexion. Squatting, kneeling and sitting cross-legged are considered very important aspects of daily routine activities for Muslim and Asian population, which the flexion can go up to 165 degrees. This is to be used to countering the problem of low flexion in common total knee replacement together with any conflicting problems that occurs in changing and improving the existing design. The objective of the project is to apply theory of inventive problem-solving Triz on existing total knee prostheses to create a new design of high-flexion total knee prostheses based on the solutions from Triz and to analyze the design using finite element analysis to verify the new concept of high-flexion total knee prosthesis. The scope of this project is to create a new design of high-flexion total knee prosthesis using theory of inventive problem-solving. The aim is to use the methods from Triz and apply to existing design of total knee prosthesis. The solution from Triz will be used which come from contradicting the feature to be improved with the feature that will become worse. Using the contradicting matrix table, the corresponding inventive principles from a total of 40 inventive principles will be generated, which will be utilized in generating a new concept design. The new concept will be designed using SolidWorks computer-aided design software. The design will be analyzed using finite element analysis with ANSYS software, then compare with thesis from another FYP student. Next is methodology. The conceptual framework in the study consists of 6 main steps, which follows problem-solving model based on Triz. Next shows the list for the 39 engineering parameters of Triz methodology. After placing the parameters, it will present with 40 invention principles to come up with an inventive solution to a problem, and every principals will have their explanation and details for making a new design. The first step is preliminary problem analysis, which is to find and gather the problems of the existing design of total knee replacement. There were 3 problems found: typical knee prosthesis available made to reach a maximum flexion up to 130 degrees, causing problems in doing activities that require higher knee flexion. The polyethylene meniscus surface suffered wear damage over time. The wear caused the meniscus to become thinner, and wear debris will accumulate on the dish surface of the meniscus, which can cause inflammation. Total knee prosthesis has high contact stress, which will cause wear. Then from that, contradiction analysis were made. The problem found to be self-interpreted into the contradiction of Triz. It will be contradicted by what characteristics to be improved with that will be getting worse. The problems were stated as for the first problem, to increase the flexion of knee prosthesis is by changing the structure of components, which leads to a problem of reducing of stability in the components. Second, to prevent any wear debris accumulating on the meniscus surface is by altering the meniscus structure, which leads to a problem of lack of stability in the knee prosthesis. The third is to reduce the femoral component's contact stress with the tibial platform is by changing the combination of the femoral and tibial platforms, which results in an increase in component numbers. Next is a contradiction elimination. The tables shows the principle that correspond to the contradiction. For the first problem, the improving feature is number 39, productivity, and the worsening feature is number 13, stability of the object's composition. There were four principles, 35, 3, 22, and 39, that correspond to the contradiction. And principle 3, local quality, is chosen, which gives the following explanation: change an object structure from uniform to non-uniform, change an external environment, make each part of an object function in a condition most suitable for its operation, make each part of an object fulfill a different and useful function. For the second problem, the principles were 13, 3, and 35, where principle 13, the other way around, is chosen and is gave the explanations to invert the actions used to solve the problem and make movable part fixed and fixed part movable. Turn the object upside down. The last problem, the principles are 12, 14, and 36. Principle 14, sphericality curvature, is chosen with the explanation: instead of using rectilinear part surface of form, use curvilinear ones. Move from flat surface to spherical ones. Move part shape as a cube to ball-shaped structures. Use rollers, ball spirals, domes. Go from linears to rotary motion. Use centrifugal force. The next step is solution evaluation. Principles 3, 13, and 14 are used to develop a new concept for the new design of the total knee prosthesis. From principle 3, the solution were to change the structure with a function where the femoral component and meniscus touch and stop at the maximum specified angle of flexion. From principle 13, the solution were to use a convex shape for the meniscus instead of the usual dish concave shape. From principle 14, the solution were using example from double enveloping worm gear. The femoral condyle will have a double enveloping contact surface which are throated and wrapped around each other. A new design created using SolidWorks, applying the solutions for a new concept of the High-Flexion total knee replacement. A new design concept using a femoral and meniscus structure that have space for a stopper at the maximum angle of flexion. A convex meniscus with a double enveloping femoral condylar contact surface is designed using SolidWorks as shown in the following figures. Next, Finite element analysis is done on the new design using ANSYS software to find out von Mises stress for varying weight at various angles of flexion. Table shows the properties of material to be used in the analysis. Titanium alloy used for femoral and tibia, and the polyethylene is used for the meniscus. The analysis were done on the angle from 0 degree to 165 degrees. Result and discussion. 3 problems were analyzed from typical knee prosthesis design. Using Triz method, the solution found were used in making the new design using SolidWorks. Figures show the new design concept using a convex meniscus shape and paired with a double enveloping femoral condylar contact surface. The meniscus usually have a concave dish surface. After applying the principle from Triz to invert the action and to turn the object upside down, it is turned to the opposite. Convex shape of the meniscus together with a concave surface of the femoral component contact surface designed so that where debris will not accumulate on the meniscus surface. Total knee prostheses usually have high contact stress. The concept from double enveloping worm gear is utilized for the new design. Both components, double enveloping femoral condylar surface and the convex meniscus surface, just like the double enveloping worm gear set, are throttled and wrapped around each other. The meniscus sliding surface remains concave in the anterior-posterior direction to conform to the shape of the femoral component. The femoral condylar double enveloping contact surface gives a smooth sliding interface between components with a large contact area. Next, typical knee prostheses usually do not have a very high flexion. The femoral component cannot flex higher due to limitation of the meniscus shape. From the principle obtained from the Triz method, the meniscus is designed to have a space at the posterior position of the meniscus and a stopper at the maximum angle of femoral component flexion. The femoral component able to flex up to 165 degrees, which then stop and touch with the meniscus surface. Here shows the cross-section of the femoral component and meniscus at the maximum flexion of 165 degrees, where both parts contacted at the stopper. Maximum targeted flexion angles can be achieved. Meanwhile, the contact surface area also high, which makes it able to have a maximum flexion for longer duration at one time. Next, I will show a little bit of simulation for the design. For the finite element analysis of the knee prosthesis, analysis were made at various loads from 50 kg to 90 kg and with various angles from 0 degrees to 165 degrees. From the table at the angle of fraction of 0 degrees or at the standing position have the lowest equivalent stress on the knee prosthesis that only varies from 8.355 to 15.04 MPa. As standing is a natural position, the contact surface is largest among the other angles of flexion. At 165 degrees, have the highest values of stress, as it was at the critical position, which varies from 45.545 to 100.8 MPa. From the graph, shows the line for the values of the equivalent stress on the knee prosthesis. At 0 degrees, the stress increased by a latent amount for each increment of the weight applied. At 165 degrees, the von Mises stress increased rapidly when the weight of the person increased. The higher the weight, the higher the stress the person that used it caused and applied on the knee prosthesis when they flex their knee. The figures below shows the mesh of the knee prosthesis when the von Mises stress that had been applied on the design, and it shows where the stress distributed on the surface of the prosthesis, from the lowest values to the maximum values of the critical point. Finite element analysis from this design were compared with design from FYP thesis paper by another student. Table shows the result from the paper. Same material and material properties were used, and with the load of 80 kg, the equivalent stress at 0 degrees knee fraction is 39.369 MPa. The value is lower than modification 2 and 3, while it has almost similar values with modification 1, with only 0.46% difference. At the flexion of 155 degrees, design from this paper have the equivalent stress of 59.902 MPa. The stress is slightly higher than modification 1, with a difference of 4.6% and lower than modification 3, while modification 2 have a very high value compared to the others. The design from this paper have almost similar results with modification 1, with only slightly higher equivalent stress at the 0 degrees and 155 degrees angle of flexion. This design have a lower von Mises stress compared to the other two design, modification 2 and 3. For the conclusion, theory of inventive problem-solving Triz is used in this paper and applied to existing design to design a new high-flexion knee prosthesis. 3 problems were found and had been solved using Triz method, contradicting using the 39 engineering parameters and 40 invention principles of Triz, creating new design using SolidWorks. The finite element analysis is done using ANSYS software with loads varying from 50 kg to 90 kg and the angle of flexion from 0 degrees to maximum of 165 degrees were analyzed. It shown that the von Mises stress increased in non-uniform state at the angle of flexion as the angle of flexion increased. The design on this paper were compared with the design from paper by Assoc. The design has similar value of von Mises stress with 1 out of 3 design and have a lower and better results compared to the other 2 designs. Triz methodology is one of the effective scientific method and systematic in making new design innovation. That's all for me. Thank you.